All right, let's go ahead and get started. This is Chapter 9, the Ideal Gas Laws. And Avogadro plays a big part in this, just like he did in the mole concept. For the ideal gas laws, let's go back and start with the kinetic molecular theory again. Now, we've seen this before. Kinetic molecular theory basically says that all substances have an inherent attraction to each other. It's called an intermolecular force and makes particles stick together. An example of this, we said, was the buckyball, little magnets stuck together. This would represent a solid. In a solid, the particles don't have enough inherent energy to overcome these attractive forces. So they just sit there and they vibrate because nothing ever sits still. But they have a defined shape, a defined volume, whatever. They don't move, they just slowly vibrate. If we put more energy in, we wind up with a liquid. In a liquid, we have enough energy to overcome some of the attractive forces, but not break them. So the particles just kind of slip and slide around. But in a gas, we put in enough energy that we can totally break all of the intermolecular force bonds, and the particles just whiz around like mad in their container. Basically, they go in a straight line until they hit something or each other. And note from the animation here, there's lots of space between the particles, and they really are moving out. All right, we're talking about gases in this chapter. So, in a gas, the gas has an indefinite shape. It takes on the shape of its container. That's because the particles just keep going straight until they hit something. That's either each other or the walls of the container. They can expand and compress. That's because there's lots of space in between them. So you can squeeze them down. And if you make the container bigger, they just keep going till they hit the wall. And finally, they're really moving out in there, aren't they? So they diffuse uniformly throughout the container. If we take a sample at one end of the container and at the other, they will have exactly the same composition. All right, as these particles whiz around and they hit things, they're going to transfer some of that energy. This is referred to as gas pressure. This is an animation. It's actually a movie from a calculation. There are 500 or so little particles here. The walls of the container are fixed, but this guy is floating. If you notice, it's kind of bouncing up and down a little bit. That's because its position is calculated based on how many collisions there are from these particles with the bottom of this barrier. So the collisions bounce it up. It kind of vibrates up and down depending upon how many particles there are. Atmospheric pressure is a result of the air molecules, a mixture of gases, striking the various surfaces in the environment. The pressure of the atmosphere is about 15 pounds of force on every square inch. Now that's huge. If we didn't have gas on the inside pushing out, we would just be squished down to nothingness. To measure gas pressure, we use something called a barometer. Now, there are lots of barometers. This is a classic weather barometer. In a classic weather barometer, typically it will show rain. This is fair weather, this is change, whatever. Um, the reason for this is that low pressure down here on the scale is associated with storms. High pressure associated with nice sunny days. And this, of course, is somewhere in between. We have these guys mounted on the lab wall, but we can't get in there, of course. Down here, we have an old-fashioned recording barometer. Back before we could record things digitally, we would take a strip of paper here, put it on this. It would slowly rotate during a day. Here's the barometer thing, and the ink would make a line up and down depending upon changes in atmospheric pressure. In the lab, we do lots of chemistry at very low pressures. This is a manometer, it's called. You put this in the vacuum line, and you can read very, very low pressures by looking at the columns of mercury on both sides here. My favorite in all these, however, is this guy. This is a sealed globe. It has air in the top here and a liquid. This is open to the outside. Now, I grew up in Florida. In Florida, you would have one of these things sitting on your shelf somewhere. The reason for that, storms come out of nowhere in Florida sometimes, especially in those days before we had satellites and stuff like that. There could be a hurricane on your doorstep before you even knew it. This thing sitting on your shelf, if the air pressure starts to get low, indicating a storm is coming, what happens is this pushes down, liquid comes up, squirts out the top, and you know you've got anywhere from a couple hours to maybe a day to get yourself together. The mercury barometer that we're going to talk about in lab uses something like this. It's a glass tube. It is filled with mercury. It is sitting in another big beaker here that's also full of mercury. The way you make this is you take your tube, you fill it up totally, put your thumb over this end of the tube, stuff it down inside the mercury, let go. Mercury is heavy, so it drops down and gives you a partial vacuum up top. The dropping stops when the vacuum equals the air pressure pushing down. You measure the barometric pressure by looking at the height of this column, H. For sea level, 0 degrees centigrade, this height is equal to 760 millimeters of mercury. This is defined as atmospheric pressure. Now, there are other units that we use for atmospheric pressure. 760 millimeters of mercury is the height of this column, but it's also referred to as 1 atmosphere. 1 atmosphere and 760 are the same thing. Sometimes you'll see millimeters of mercury written as torr, T-O-R-R, but 760 millimeters of mercury is exactly equal to 760 torr. We're going to stick with millimeters or atmospheres in this course. As we said, 760 is also equal to about 14.7 pounds per square inch, but we'll never use these units in the class. Any questions?
No.
All right, say we're given a pressure in atmospheres and we want to convert it to millimeters. The conversion unit here is simply 760. Multiply atmospheres by 760 and you get millimeters. To go the other way, you simply divide by 760. All right, Let's begin our discussion of the gas laws by talking about the pressure-volume relationship. We'll see that this is called Boyle's law. Remember, gases can be compressed and expanded in response to increase or decrease in pressure. What Boyle says is the volume occupied by a fixed quantity is inversely proportional to the applied pressure. We're going to use this little piston to demonstrate this. This is a sealed unit. There's a gas inside. There's a piston, goes up and down, has a platform. We have a gauge over here that we can use to measure the pressure. All right. Let's say that we have our thing sitting here and we put something with very little mass on it, very little pressure, no change in our dial here. But if we put something substantial on it, like an anvil, we see the piston goes down, the volume decreases. Once again, the pressure increases and the volume decreases. That's an inverse relationship. The greater the pressure, the smaller the volume. Now, this is a little movie that's going to say the same thing I just did. Here's our same cylinder. What we're going to do is drop the cylinder slowly. The volume will decrease, and as it does, the pressure will increase. However, the volume can never drop to zero, can it? Because the gas particles have an inherent volume of their own. So we expect this to be a nonlinear relationship. Let's watch. We're starting to drop, pressure is starting to go up, and sure enough, it is nonlinear. Now, if we collect data from our dial here and plot volume versus pressure, just like this, we get this curved plot that looks something like this. If you're a mathematician, you would look at this right away and say, oh, that's a hyperbola. Okay, but it's not a straight line. The mathematical equation describing a hyperbola involves a factor of x to the minus 1. What that basically means is that it's a reciprocal relationship. As pressure increases, volume decreases. So if we take these same data, and instead of plotting volume versus pressure, we do volume versus 1 over pressure, we get a straight line. Everybody likes a straight line. This is called a reciprocal plot. This is the actual observed data. All right, so we got a straight line. That's good news. That means mathematically we can represent these data by an equation. We can say that volume is directly proportional, the little alpha stands for directly proportional, to 1 over p. That's a straight line. Now, whenever we have a proportionality symbol like this in an equation, we can get rid of that simply by putting in an equal sign and a constant. Equal constant is the same thing as proportional. If we take this expression and rearrange it a little bit, we can say PV is always going to be a constant. Multiply both sides by P, PV is equal to a constant. All right, let's look at our two examples. For our first one, we have one initial state. The pressure times the volume is going to be equal to a constant. Because this is the initial state, we'll call this P1 and V1, and it's equal to a constant. Now, this is exactly the same system, isn't it? We've just changed the pressure. Therefore, in this, we can say P2, the final state, multiplied by V2 is equal to a constant. But this constant and this constant are the same thing. If they're both equal to the same thing, we can write P1 V1 equals P2 V2. This is our first gas law. Any questions?
No.
This is referred to as Boyle's law, and this is referred to as Boyle. Robert Boyle, he was an Englishman. Doesn't look like a real friendly sort of fellow, but he was apparently quite good. He was generally regarded as the first, quote, modern chemist because he was very careful in his calculations, his measurements, things like that. Boyle's P1 V1, P2 V2. So let's see how we apply this to problems. Let's say we have 12.5 liters of a gas, and our pressure is 0.82 atmospheres. We're going to change the pressure to 1.32. We're looking for the final volume. Now, this is a classic Boyle's law experiment. P1 V1, P2 V2. What we're looking for here is the final volume. That's V2. Going to start off with this equation and solve it for V2. V2 is here. That means that it's equal to P1 V1 over P2. Now, P1, 0.82, V1, 12.5, P2, 1.32. Atmospheres will cancel. Simply multiply 0.82 times 12.5 divided by 1.32. Our final volume is 7.8 liters. Any questions? Obviously, it's important that the pressure units be the same, the volume units be the same, so that they can cancel as you work your equation. Let's do another one. We have 150 milliliters of CO2, but it doesn't matter what the gas is. The pressure is 35 millimeters of mercury. The volume is decreased to 50 mils. What's the final pressure? Once again, it's Boyle's law, P1 V1, P2 V2. Here we're looking for the final pressure. That's P2. Take our basic equation. We're looking for P2. That's going to be P1 V1 over V2. Our pressure was 35 millimeters. Our volume was 150. The final volume was 50. We do our substitution. Milliliters are going to cancel here. Again, it's important that all of these units match on both sides so that we can cancel. 35 times 150 divided by 50, 106 millimeters of mercury. Now, if I had asked you what this was in atmospheres, what would you do? Well, you would remember the magic number here was 760. 760 millimeters in an atmosphere. Therefore, we simply divide this by 760 and we get atmospheres. Any questions?
No.
All right, there are 3 tutorials in this chapter, and actually I believe these are the last 3 tutorials for the semester. Enough said. Boyle's law, a gas system has initial pressure and volume, 5 atmospheres, 5,050 mils. We're changing our volume to 5.62 liters. Obviously, we're going to have to match up our units here. What's the resultant pressure in atmospheres? We have atmospheres, so good. The way I do these, once again, is to make a list of what I know and what I don't. We know P1, 5 atmospheres. We know V1 is 5,000 mils. V2 was given in liters. We could either change this to liters or change this to milliliters. Doesn't matter. Let's just multiply 1,000 to get 5620 milliliters. So we're solving here for P2. P2 is going to be equal to P1 V1 over V2. Simply take our numbers from our list, substitute them in. We wind up with 4.538, but we're dealing with 3 significant figures, so let's round it down, 4.54. Any questions? Let's try another. We have initial pressure and volume of 2350 millimeters and 8520 mils. The pressure changes to atmospheres, so we're going to have to adjust atmospheres in millimeters. And we're looking for the volume in liters. So milliliters and liters, we're going to have to do something here as well. Make our list of what we know and what we don't. We know P1, 2350 millimeters. P2 here was given in terms of atmospheres. We can simply multiply it by 760 to get millimeters. Likewise, we could have divided this by 760 to get atmospheres. Doesn't matter. Let's take our milliliters and make liters out of it because we want our answer to be in liters anyway. So we're solving for V2. Remember, 760 is our magic number. Solving here for V2. P1 V1 over P2. Here's the thing. Looks like I left this in terms of millimeters. There we go. 3.58 liters. Any questions?
I think I was doing those tutorials today, and I think those are also the ones that where if you don't put the abbreviation for it, the unit,
Right,
it'll mark it wrong too.
that's right. Never put in units. Never, never, never. All right, so much for pressure volume. Let's look now at temperature volume relationships. Temperature volume relationship. We're going to start off with a balloon to show this guy. And we're going to dump liquid nitrogen all over. Liquid nitrogen minus 196 centigrade, very, very cold. So this poor balloon is going to get very cold as we do it. As the temperature here begins to decrease, the volume of this balloon is going to drop. This will drop down to a miserable little size. Then the nitrogen starts to evaporate, the balloon starts to warm back up, and as it warms up, by George, it more or less returns to its former glory. What happened here? Temperature went down, volume went down. Temperature went up, volume went up. It's a simple linear relationship. Again, temperature increases, volume increases. A simple linear relationship. Now, playing with balloons and liquid nitrogen is lots of fun. But chemists like to make plots and do experiments and plan things out and whatever. So what we're going to do here is take a container of gas. We're going to drop the temperature, keeping the pressure constant, and look at the effect on the volume. We're going to do this with various quantities of gas. Doesn't matter which gas it is. Remember Avogadro. Doesn't matter which gas. So let's start off with 0.25 moles of some gas. And sure enough, as we drop the temperature, the volume decreases. Now, one line is good, but two lines are better. So we now do the same experiment with half a mole of gas. Again, it's linear. Temperature drops, volume drops. 3 lines is even better than 2. 0.75 moles. Linear, temperature drops, volume drops. Well, that's good. That's what we expected. But I want you to look at these lines. Look down here. They all look like they're going somewhere. Down in here somewhere. In fact, if we take these lines and extrapolate them down, we see that all of these intersect at exactly the same point. This magic temperature is minus 273.15 centigrade, and it's the imaginary point at which the volume of the gas would drop to 0. Now, you can never get there, but if you could, the volume would be 0. This temperature right here, minus 73, is what we refer to as absolute 0. And we define a new temperature scale based on that, where this is 0 Kelvin. So that's where absolute 0 comes from. Extrapolate down till the volume would be 0, that is absolute 0. Now the Kelvin scale here is very important. We'll talk a little bit more about this. You must use the Kelvin scale whenever you do a temperature volume calculation, but that's later. All right, what we said mathematically about temperature volume, they were directly proportional. Now remember, whenever we have a proportionality, we can put in an equal and a constant. It's called a direct linear relationship. Let's take and isolate this constant. And when we do, we can say volume divided by the temperature is always going to be a constant. So for a system like our balloon, volume divided by temperature is a constant. The two states in our balloon, down here, initial state, V1, T1, gives us a constant. V2, T2, the full balloon, gives us the same constant, therefore they're equal to each other. This expression right here, V1 over T1, V2 over T2, is referred to as Charles's law. Now this is Charles, Jacques Charles. He's a Frenchman. Um, looks like a nicer guy than Boyle, but that's being judgmental, I suppose. When I first saw this picture, I thought to myself, he looks like somebody I've seen before. Anybody remember who Barry Manilow is or was? I don't know. Anyway, Charles is an interesting guy. He's described as a scientist, an engineer, and a balloonist. In fact, balloons fit. In fact, he's credited with being the first one to make a commercial-sized hydrogen balloon. This is a etching of this thing. Here's the balloon. Here's our hydrogen generator. Now, these things really kind of neat because hydrogen has such a low density that this has enormous lifting power. Everybody was happy with hydrogen balloons for a very long time until about 1937 when the Hindenburg, a dirigible with hydrogen inside, burst into flames over New Jersey. Not a nice thing. Nobody used hydrogen since. Any questions? All right, back to temperature. We all know that water freezes at 0 degrees centigrade, boils at 100. Remember our intercept was minus 273. That means on the Kelvin scale, 0 degrees centigrade is 273 Kelvin. 100 degrees, 373 Kelvin. Now these are odd numbers, I suppose, but you should note that there's 100 little degrees in between these two, just like in centigrade. So the conversion is actually very simple. They differ by a factor of 273.15 degrees. Remember, centigrade and Kelvin are always different, and they always differ by 273.15. You take centigrade, add 273, you get Kelvin. Now, because we have to know how to do this to gas law problems, let's just practice a simple set. Here we have temperatures in centigrade. Quickly, let's write the Kelvin equivalent. Remember, Kelvin is always larger than centigrade by a factor of 273. Centigrade is little, Kelvin is big. So 1,000 degrees centigrade, we add 273 to it. Minus 150, same thing, we add 273. 100, we saw this on the last slide, boiling point of water, 373 Kelvin. Any questions? All right, here's a typical Charles law problem. We have a 50 sample of gas. Our temperature is 26 centigrade. Now, right away, we know we can't use centigrade. We have to change that to Kelvin. We're going to warm it up at constant pressure until the volume is 62. What is the final temperature? Classic Charles law. We know V1, T1. That's V1, T1. And we know V2. That's this. We're looking for T1. I guess that should be V2, the final temperature of the gas. This is Charles's law, right? We're looking for the final temperature. That's T2. V2, T1 over V1. V2 is no problem. It's right here in mils. Mils and mils match, so that's good. T1, however, was given in centigrade. We know we have to change that to Kelvin, and we do that by adding 273. Makes it essentially 300 Kelvin. Going to divide this by V1, that's 50 mils. Our milliliters are going to cancel. 62 times 300 divided by 50. We have too many numbers in our answer here. We're dealing with three significant figures, so let's round this to 374. Now, what if I asked you what this was in terms of centigrade? How would you do it? Kelvin minus 273 is centigrade. Any questions? Charles' Law tutorial. Gas system has initial volume and temperature of 11,000 mils, 106 centigrade. Again, right away, we know we're going to have to fix this. The volume is going to change to 7.6 liters, so we're going to have to adjust this so liters and milliliters are the same unit. And we're looking for the final temperature in Kelvin. Okay, once again, make a list of what you know and what you don't know. V1 was given in terms of milliliters. V2 was given in terms of liters. We could make this liters. We could make this milliliters. Let's just do it this way. 7.66 liters, 7660 milliliters. This is our given temperature in centigrade. We add 273 to make it 379. And finally, we're looking for T2. T2 is going to be V2 T1 over V1. Look at your list. V2 T1 V1. Substitute in. Solve it. 264 Kelvin. If we wanted this in centigrade, we would subtract 2C3. Any questions? All right, well, let's go back to our plot. You know, it looks like a nice simple plot, but doing an experiment like this really is a lot of work. Okay, lots of measurements, lots of setup and whatever. After you do something, you want to make sure you get all the information out of it that you can. So let's add another question. If we kept the temperature constant and simply changed the number of moles, what's our relationship? So what we'll do is just take these data, constant temperature, different amounts of gas. When we do that, we wind up with the mole-volume relationship. Now a prediction here kind of makes sense. More gas you add, bigger the volume. In fact, that's what we see. Here's our volume, here's the number of moles. This is referred to as Avogadro's law. Volume and the number of moles are directly proportional. Okay, so we have three gas laws, three independent gas laws: pressure volume, temperature volume, and mole volume. Here's our list. Boyle said volume was proportional to 1 over P, inverse relationship. Charles said volume was directly proportional to T, simple linear. And Avogadro said volume was directly proportional to the number of moles. Well, if volume is proportional to all of these guys individually, if you combine these into one expression, volume is proportional to NT over P. So, if we want to get rid of our proportionality here, what do? We put in an equal sign and a constant. Okay, but you know what? I'm really tired of using K as a constant. It just gets boring after a while. So instead of using K, I'm going to use an uppercase R, and I'm going to call it the universal gas constant, R. Just a constant instead of K. This is our ideal gas law expression. Volume would equal this constant R times NT over P. Well, this is a valid expression, obviously, but nobody ever writes it this way because there's a much more fun way to do it, and that is to write it this way. PV equals nRT. It just kind of flows, doesn't it? Kind of like an internal rhyme or something. PV equals nRT is our ideal gas law. This means that if we don't know one thing here, we can simply solve for it and get our pressure, our volume, our temperature, or our moles. Or at least we could do that if we knew what in the world R was. What's our constant? Fortunately, Avogadro helped us out here. Experimentally, way back when we were talking about moles, we remember that Avogadro said, if you have any gas, it doesn't matter what it is, and you have 22.4 liters of it at 1 atmosphere and 373, that is equal to 1 mole of the gas. The mass is the formula mass. So 1 mole is our temperature, Kelvin. Pressure is 1 atmosphere, and our volume is 22.4 liters. Knowing this, we can calculate R. R is going to be PV over NT. Again, P is 1, volume is 22.4, N is 1 mole, and T 273 Kelvin. Now, if you notice here, nothing cancels, does it? So the units of R are going to be atmosphere liter per mole per Kelvin. And the number's awkward too. It's 0.082 liter atmosphere per mole per Kelvin. I have trouble remembering this too. And I assure you, anytime you need the value of R on an exam or a quiz, I will give it to you. 0.082 liter atmosphere per mole per Kelvin. Any questions? Well, let's see how we use this. How many moles of argon are there in 18.6 liters of a container? We're at 293 Kelvin, and our pressure is 2.35 atmospheres. What we don't know here is the number of moles, and that's N. So we start with PV equals nRT. We're looking for N. N is going to be PV over RT. Our pressure here 2.35 atmospheres. Our volume, 18.6. R, 0.082, is a constant. And T for our temperature is 293. So pressure, 2.35. Volume, 18.6. R, 0.082 liter atmosphere per mole per Kelvin. And finally, our temperature, 293 Kelvin. We're looking for number of moles. Atmospheres will cancel. Liters will cancel. Kelvin and per Kelvin, that's 1 over Kelvin, will cancel. This is mole to the -1 in the denominator, so it comes up top. Our calculation gives us 1.81 moles of argon. Any questions? All right, this is the ideal gas law tutorial. There are two ideal gas law tutorials, a quote single state and a dual state, two-state. In this course, we are only going to do single state. So you're looking for the tutorial. It's PV equals nRT. We have a gas system that has volume, moles, and temperature. 5 liters, 0.396 moles, 291 Kelvin. What's the pressure in atmospheres? Okay, we're going to simply take PV equals nRT and solve for pressure. We don't know what the pressure is. The volume is given in liters. N is given in moles. Temperature is given in Kelvin. So we're good. Whenever you use PV equals nRT, you must have atmospheres, liters, moles, and Kelvin. If you don't have them, you have to change to them. Atmospheres, liters, moles, and Kelvin. We're going to solve for P. That's nRT over V. N, R is our constant, 0.082. T is our temperature, and that's our volume. 1.86 atmospheres is what we get, and that's our answer. Any questions? Remember, if the thing had come up and instead of asking you for the pressure in atmospheres, it asked for millimeters, all you would do is multiply this by 760 to get millimeters of mercury. 760's our magic number. One more here. Gas system is pressure, volume, in moles. 1.5 atmospheres, 8,000 mils, and 706 moles. What's the temperature in Kelvin? Remember, this has to be in liters. Here's our list. We must change milliliters to liters. Here's our pressure. Here's our number of moles. And we're looking for the temperature. Temperature is going to be PV over nR. So P, V, N, and again, R is our constant, 0.0821. Do our simple calculation here, 225 Kelvin. Any questions? All right, some exam questions here. Under conditions of fixed temperature and amount of gas, Boyle's law requires what? Basically, what we're saying is, which of these is Boyle's law? Well, we remember Boyle told us P1 V1 is equal to P2 V2. Well, this is Boyle's law, isn't it? As written. Turns out all of these can be correct. This is Boyle's law as written. Now, in order to get here, remember we started off saying pressure times volume was a constant. So this is correct too. This guy, if you take P1 V1 equal P2 V2, you can divide by P2, divide by V1, and you get this expression. So this is valid as well. Okay, all of the above are correct. There's a story for this question. Many years ago, I was teaching an intro chem class with 500 people in it, 8 o'clock in the morning, and the exam was coming. I wanted to be a nice guy, so I put this question on the exam because I figured this was so simple, everybody would get it. So it's a gift, being nice, right? Turns out that out of the 500 people, virtually everyone missed it. Yeah, I couldn't understand either. So I put this question, or one like it, on virtually every exam I've given since. Sometimes it's Boyle, sometimes it's Charles. Let's look at Charles' version. Charles' law requires what? T1 V1, T2 V2? No, that sounds a whole lot like Boyle, doesn't it? This is Charles. V1 over T1, V2 over T2. So this is wrong. TV isn't a constant. V over T is a constant. And finally, if you take this expression, there is no way you can rearrange it to make T over T equal V over V. Nope. Algebraically, doesn't work. None of these are correct. So I can assure you that on exam 2, you will have a question for either Boyle or Charles that will be some perturbation on this question. Any questions about the question? Standard calculation here. Pressure 450, pressure of 450 mils in 1 atmosphere. We reduce the volume until the pressure is 5 atmospheres. What's the resulting volume? This is a Boyle's law problem, isn't it? So we're going to do P1 V1 equal P2 V2. We are looking for the resulting volume, that's V2. We substitute. This is P2, this is P1 V1, and we're dividing it by P2. Do the calculation. Atmospheres cancel. We're at 90 mils. And finally, this is also meant to be a very simple question. When comparing centigrade and Kelvin, which of the following statements is true? 1 Kelvin is a larger temperature change? No, remember they're exactly the same. Celsius or centigrade and Kelvin are never numerically equal. That's correct, isn't it? Because they're always 273 degrees apart. Only centigrade can be converted to Fahrenheit. Well, that's stupid. So remember, these are always different. Kelvin is always larger than centigrade. So let's just wind this up by talking about the kinetic molecular theory again. We're going to see some little movies that kind of explain the basic gas laws. Remember, gas consists of molecules in constant, random, and very fast motion. Pressure arises from collisions with a container. In an ideal gas, there are no attractive forces, and the volume of the molecules is negligible. So these are the assumptions. Avogadro and the KMT.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
Sometimes it sounds much more official when a woman says it, but what this is simply saying, we've doubled the number of molecules, but we kept the box the same size. We get twice as many hits on the walls. Pressure and number of moles are directly proportional.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
As you raise the temperature, the speed of these little guys goes up. They have more energy, hit the wall harder, temperature goes up, pressure goes up.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
Here we have dropped our volume. The number of hits goes up, so the pressure goes up. So the volume goes down, pressure goes up. Inversely proportional. Any questions?
No.
All right, well, I believe this winds it up for the tutorials for the second half of the semester. There are a bunch here. Today we've added Boyle, Charles, and ideal gas. Once again, go to Chemistry Online Practice, go to Blackboard, and take it. Very important to make sure you get enough points in order to get out of taking the final. So do all these extra credits as best you can.